Picture this. 9 out of 10 students write down what looks like a perfectly logical binary sequence. And boom, they quietly lose their top grade without even realizing it. They literally walk out of the exam room feeling super confident, but they've just stepped right into a massive trap. Let me show you exactly what this mistake is before you end up making it yourself. So, take a look at the sequence on the left side of your screen. 1, 0, 0, 1, 0, 1, 1, 0, 0. Now, that's 9 bits, but in a standard 8-bit binary addition scenario, that right there is what we call the overflow trap. Before we get into the absolute best solution for crushing this exam, we have to recognize the root of the problem, right? You just cannot cram 9 bits of data into an 8-bit space. It literally breaks the system and causes an overflow error. Okay, let's break down exactly how this works. I want you to focus on the blue box right in the center of the image. That's the successive division method. It's exactly how you correctly convert a denary number, like 121, straight into binary. You just divide by 2, track your remainder, and read it from bottom to top. Pretty simple, right? But now look over at section 3 on the right. When you add the binary for 109 and 90, you get 199. Totally fine. But if you try to add 200 and 100, you get 300, which actually generates a 9th bit that simply can't fit. Boom, overflow error. Now, obviously, this shows us the mechanics, but there's this one hidden detail, a really specific way of structuring your answers that is absolutely mandatory for full marks across every single paper 1 topic, from binary all the way to hardware. I'm going to leave you hanging for just a bit on that one, though, because I'll be revealing that secret ingredient at the very end of this explainer. All right, moving right along to our next section, mastering internet risks, the 3-layer fix. Because whether you're dealing with a binary overflow or some nasty malware, fixing the mistake always requires a really structured approach. To bag those top grades, you can't just write your answers like you're texting a friend. We need to use what's called a 3-layer learning model. Step 1 is to identify and classify. Step 2, sequence the explanation. And step 3 is contextual specificity. This is exactly how we shift from everyday casual chatting into precise, exam-ready technical vocabulary. Let's see this in action. Take a look at the banking scenario graphic up on the right. When an exam question throws an internet risk at you in a banking system, you absolutely cannot just write, "Oh, hackers can steal money." Nope. Instead, you apply the 4-prompt strategy you see right there at the bottom. You ask, what is it? How does it work? Where is it used, and why is it chosen? By laser focusing your technical knowledge directly into that specific banking context, you instantly lock in those deeper, high-level marks. Okay, let's transition over to the hardware side of things for a second. Inside the CPU core, avoiding the generic response. The CPU is honestly where students lose just an unbelievable amount of marks, mostly by throwing down these overly generic textbook answers that examiners have already seen literally 1,000 times today. So, your first major goal here is to secure a super solid Cambridge-safe definition of what the CPU actually does. The CPU core purpose is the central component executing instructions using the fetch, decode, execute cycle within a scenario context. Did you catch that last part? Not just inside a computer, but within a highly specific context. Let's look at the visual mechanics of how this actually plays out. This image right here brilliantly illustrates the exact reasoning pathway you need to take. Just let your eyes follow that gray path across the screen. Notice how it starts by classifying the requirements, then it sequences the explanation, and then, this is crucial, it anchors the whole thing to a digital scenario, like that robotics factory or the banking app you see at the top. So if the question is talking about a robotic arm in a car factory, your CPU explanation has got to mention how it processes data specifically for that robotic arm. I want you to really burn this rule into your brain. Description names the concept. Explanation details how it works and why it matters. I really can't emphasize this distinction enough. Merely naming a process, like just writing down fetch, decode, execute, is literally never enough to secure those deeper marks. You've got to explain the how and the why. See that red warning triangle over on the right? That right there diagnoses the classic generic response pitfall. The absolute most common mistake students make is completely missing the process stops. They just skip vital steps in their explanation. You have to lean on layer 3, which shapes your technical knowledge into this really concise step-by-step sequence that is specifically designed to score points when you're sweating under time pressure. Let's turn this into an interactive test, shall we? Fetch, decode, execute, the 10-second challenge. We're going to do a quick, high-stakes, pause and solve challenge right now to really test your grasp of the FD cycle under a little bit of pressure. Okay, here is your question. Which contrast pair correctly distinguishes memory versus storage in the fetch, decode, execute cycle? I want you to literally pause this explainer right now, start a 10-second countdown timer in your head, and actively apply the method mark strategy to spot the correct distinction. Go. All right, time is up. Let's reveal the answer. Cast your eyes down to the bottom right corner, right there at the orange contrast pair box. The correct pair cleanly separates memory, which handles internal processing like holding the actual instructions being fetched right now, from storage, which is all about long-term data retention. Using this method mark strategy ensures you explicitly separate the what from the how and why. Awesome. We are moving into our final technical topic now. Registers and problem solving, the final layer. Let's keep this momentum going by immediately pinpointing exactly what the exam demands from you when it comes to registers. Focus on phase 2 on the right side of your screen, the structured solution path. Notice that top step, identify and classify, selecting the exact register needed for a specific exam scenario, whether that's the program counter or the accumulator, is pretty much the ultimate test of your knowledge here. You can't just know what a register is in a vacuum. You have to pinpoint the exact one the question is demanding and then explain it in that specific context. Now, here is a massive trap you absolutely need to avoid. Look right at the middle column. Wrong turn to validation versus verification. Validation checks if data is sensible, whereas verification checks if it matches the original source. This brilliantly illustrates how easily nearby, sort of similar concepts can completely sabotage a perfectly good technical answer if you get them twisted. You have got to lock down those definitions for sure. Wow, okay, we've covered a ton of ground today, so let's bring it all together. The ultimate exam strategy, the hidden detail revealed. It is finally time to close that curiosity loop I opened in the very first minute of this explainer. So what actually is the one secret ingredient required for top marks? Drumroll please, here it is. The hidden detail is contextual specificity. You must apply the 4-prompt strategy strictly to the scenario provided. 1, what is it? 2, how does it work? 3, where is it used? 4, why is it chosen? And 5, contextual specificity. If the exam question is talking about an automated greenhouse, your answer absolutely must mention the greenhouse. No generic textbook answers allowed. It's got to be understood, not just memorized, you know? And hey, definitely don't stop studying now, because you really need to see how this exact contextual framework applies to algorithm trace tables. Click on our next explainer right now, because once you see how trace tables work with this 4-prompt strategy, your programming logic is going to become completely bulletproof. But ask yourself this: if you master all this hardware but fail to articulate the logic behind it, what good is the knowledge? Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE, to excel in your Cambridge examinations. Catch you in the next one.